Patty Simpson with Simpson Math. In this video, we're going to look at two-way tables. So a two-way table organizes data collected from two different variables, usually qualitative or categorical variables, and examines the relationship between that bivariate data. When we talk about two variables, we use this word bivariate. So we're going to look at the data collected from two different variables and put them on a two-way table to be able to examine that relationship. So here's a scenario where we might use a two-way table. Researchers gather measurements from athletes and spectators at a charity 5K run and organize the information on this two-way table. So here I have two different variables. In our two-way tables, we'll put one variable, the data collected or the answers to one variable along one side, and the answers collected from another variable along another side. So here along the top, our variable is what is the position of a person at the 5K. And those people would either be athletes or spectators. So this is the position that they held at the 5K. Then along here is our other variable. So at the 5K, we took measurements from them, and those measurements were of blood pressure. And when we measured their blood pressure, we put them into two categories, either high blood pressure or normal blood pressure. So along here, the variable is what was their blood pressure, normal or high. So now that we have our two variables on the chart, then we begin to fill in the chart. And our chart should always, in a two-way table, your columns should add up. So this, the number of athletes with high blood pressure or normal blood pressure, and the number of athletes with high blood pressure should add up to be the total number of athletes. Your number of spectators with normal blood pressure and the number of spectators with high blood pressure should add up to be the total number of spectators. So here we know we had 20 total spectators. That's what that 20 tells us. And this is the total number of our blood pressure. So we had 10 people, athletes and spectators, 10 people had normal blood pressure. This too is the high blood pressure and an athlete. So we had two athletes with high blood pressure. This bottom is the total number of athletes and spectators and the total number of people who attended our 5K. So we had 30 total people that attended the 5K. We've only filled in a few of the values, but once we have a few of the values, we can fill in the rest just by adding and subtracting. So here, if I know I have 30 total people and 10 of them had normal blood pressure, if I do a little subtraction, I can find that 20 people had high blood pressure. Again, if I have 30 total people and 20 of them were spectators, then with a little subtraction, I can find out that I had 10 athletes. I had 10 total athletes, 2 of them had high blood pressure. That tells me that I had 8 people with normal blood pressure. 8 athletes with normal blood pressure. Then, if I had 10 total people with normal blood pressure and 8 of them were athletes, that means 2 of them, subtracting, were spectators. So 2 spectators had normal blood pressure. And again, just subtracting, this 20 total people with high blood pressure, 2 of them were athletes. That means that 18 were spectators. Notice that I can add up my columns and add up my rows, and it all adds up. 8 plus 2 is 10, 2 plus 18 is 20, 10 plus 20 is 30. This direction, 8 plus 2 is 10, 2 plus 18 is 20, and 10 plus 20 is 30. So my columns and rows have to add up. Then I can begin to look at the two-way table and notice certain relationships. Like, for instance, more of the people with high blood pressure were spectators, whereas my athletes had more normal blood pressure. So that's how we compare the relationship then between those two variables. So there's an example of a two-way table. In our next video, we'll continue to look at some examples of two-way tables. In this video, we're going to look at some vocabulary that we use when we are talking about medical tests. So we all go into the doctor at some point throughout our lives and have a medical test run. So maybe we go in and they look for the flu, or they swab us for strep throat, or as a woman, I go in and have a mammogram done. And we get back test results that say you're positive for the disease or you're negative for the disease. Well, sometimes those results are actually wrong. We may get a positive result back and it turns out we don't have the disease, or we may get a negative result back and it turns out we did have the disease. So when we are talking about those tests and those results, we use certain words to help us with that. So the first word we're going to look at is this word prevalence. And the word prevalence just means how often does the disease show up in the population. So the prevalence is the percentage of the population that is affected with a particular disease at a particular time. So for instance, here, the prevalence of a disease is 1%. How many people have the disease? Well, it depends on the size of our population. 1% of the population is expected to have that disease. So if I have 100 people, 1% of 100 is just 1. That's what 1% means. It means 1 out of 100. So 1 out of every 100 people would be expected to have that disease. If my population is larger, let's say that my population is 1,000. Notice I multiplied my denominator by 10. I just multiplied my numerator by 10. Because 1% of 1,000 is just 10. I would expect 10 people to have the disease out of 1,000 people. And if I had 10,000 people, well then I would expect 100 people to have the disease. So I just take my population and multiply it by 1% to find out how many people in that population should have the disease. So that's what the word prevalence means, is how many people out of your population should be affected by this disease. Then we have the sensitivity. The sensitivity of the test just tells of the people who have the disease, what percentage of those will the test show they actually have the disease. We call that the true positive. So in medical diagnosis, it's the ability of the test to correctly identify those with a disease, the true positive rate. So again, for instance, if we have a test that has a sensitivity of 90%, how many people with the disease test positive? Well, if 100 people come in with the disease, what that means is that 90% of the time, the test is going to show that they have the disease. They're going to walk out with a positive test. So 90 out of the 100 people with the disease walk out with a positive test. Now, if my population is larger, let's say I have 1,000 people with the disease, well then 900 of them walk out with the test, with a positive test. If 10,000 of my people have the disease, then I would expect 9,000 of them to walk out with a positive test, positive result. Notice though that some of the people who have the disease walk off with a negative test. 10 of them may walk out and their test said negative even though they have the disease. That is called a false negative. They have the disease, but the result says negative. They got a false negative. Here, the specificity is the ability of the test to show a true negative. In other words, if I walk in and I do not have the disease and they swab me, what's the rate of those who actually get a negative back? If I don't have the disease, I should get a negative. Well, in medical diagnosis, the specificity is the ability of the test to correctly identify those without the disease. We call that the true negative. So here, the test specificity is 80%. How many people without the disease test negative? So I walk in, I don't have the disease. If there are 100 people who walk in without the disease, 80 of them we expect to walk out with a negative test. Now that means that 20 of them are walking out with a positive test. That positive test is called a false positive. It's not a real positive because they don't have the disease. So that's how specificity, sensitivity, and prevalence works. So those are our true negative, our true positive, and this is just how often it shows up in our population. Also know that there is a false positive, so I could get a positive even though I don't have the disease, and I could get a negative, a false negative, where I get a negative when really I do have the disease. We're going to use this vocabulary as we build two-way tables and we look at Bayes' theorem here in the future. In this video, we're going to create a two-way table. So here we have a certain virus infects 1 in every 200 people, or we have a 0.5% prevalence, how often it shows up in the population. A test used to detect the virus has a sensitivity, true positive rate, of 80% and a specificity, a true negative rate, of 95%. Create a two-way table to represent the data. So first, with the two-way table, we know that we have two variables. The first variable here, if it's prevalent in 1 out of every 200 people, that means that some of the population has the disease and some of the population does not. So our first variable is, do they have the disease or not? I'm going to put the answers to that along my first row. So they have the virus or they do not have the virus. And then my total. So as I'm creating my two-way tables, this is the first thing I need to do is figure out what are my two variables. So that's one of the variables. The other variable, well, the test is going to detect whether or not they have the virus. So as a person who goes into the doctor to get a test, I'm going to get one of two results back. I'm either going to get a positive or I'm going to get a negative. So the other variable here is, what is my testing result? Positive or negative? So along this first column, I'm going to put that other variable. I test positive, or I could test negative. And then the total number here. So as I create my two-way table, the first thing I have to determine is the variables in my situation. What variables am I collecting data on? Then I'm going to start to fill in this two-way table. And I'm going to use the information I have. First of all, I know that the virus infects 1 in every 200 people. So how many people have the virus? Well, it depends on my population. So if my population is a population of 200 people, if I have 200 people, then I know 1 of those people has the virus. So I could put 200 in my total, and 1 would have the virus. That means that 199 of those people would not have the virus. But maybe my population is larger than that. Maybe my population is 2,000 people. Well, if 2,000 people are in my population, then 10 people would have the disease, and that would mean 1,990 would not. Notice that all I have to do there, if I add a 0 there, I'm adding a 0 there, and I'm adding a 0 there. Again, if my population is larger, say my population is 20,000 people, then that means that I would expect 100 of those people to have the disease. Again, if I have 20,000, I add a 0 there, I add a 0 there, I add a 0 there. So if there are 20,000 people in my population, then I would expect 100 of them to have the disease and 19,900 of them not to have the disease. Then, the next part of my question says, a test used to detect the virus has a sensitivity, a true positive of 80%. So in other words, those people who come in and actually have the disease, 80% of them we expect to walk away with a positive test. So on our chart, 100 of them have the disease. We know from the sensitivity then that 80% of those will walk away with a positive test. So since I have 100 of them with the disease, 80 of them will walk away with a positive. That's the true positive. That's the true positive rate. That means that out of those 100, 20 of them walked away with a negative test. They actually have the disease, but they walk away thinking that they do not have the disease. Then we look at the specificity, and the specificity is the true negative. So the people who walk into the office without the disease, they're tested, they should walk away with a negative test. And 95% of the time in this particular test, they do walk away with a negative test. So of those 19,900 people, we can find 95% of that. So you just do 95% times that 19,900. Or, let me grab a eraser. Let me make it a little bigger here. So remember, if I'm doing percent, I'm going to make it 95 over 100, because that's what percent is, times 19,900. I can make these zeros become 1. So now I'm just multiplying 95 times 199. So I know that 18,000, multiply that out, and 18,905 people are going to walk away with a negative test. Those 19,900 that walked in without the disease, 18,905 of them are going to walk away with a negative test. But that means that 995 people, subtract there, 995 people walked away with a positive test. They walked away thinking they had the disease when they didn't. So we had a total of 1,075 positive tests, and we had 18,925 total negative tests. This should add up to be that column. So you can always check yourself, make sure that this adds to that, this adds to that, this adds to that, and then across they should all add up as well. So there is our two-way table for this particular scenario. In the future, we're going to look at using Bayes' theorem to determine the probability that we actually have a disease if we're given a positive test, or the probability that we have the disease if we have a negative test. In this video, we're going to create a two-way table. Marie is getting married at an outdoor ceremony in the desert. In recent years, it has rained only 5 days each year. When it actually rains, the weatherman predicts it rains 80% of the time. When it doesn't rain, he incorrectly forecasts rain 10% of the time. Marie used the information to create a two-way table. So that she's planning for her wedding, she's displaying various data to help her make her decisions about the wedding. And here she creates a two-way table based upon that rain. So she's looking at all the different days within the year and trying to decide, is it raining or not raining? So the first variable she's looking at is the weather. Does it rain or not rain? So I'm going to put that variable here along the top. So it rains or it doesn't rain. So we're looking at how many days each year that happens. Then she wants to know, of those days that it rains or it doesn't rain, what does the weatherman do? How does he handle that? Well, sometimes he predicts rain and sometimes he predicts no rain. So our other variable is the weatherman's actions. He either predicts rain or he doesn't predict rain. So that would be along this column. Predicts rain or he predicts no rain. Once we have our variables, remember that both the row and the column has to have a total. There has to be a total column and a total row here. So that when we make our two-way table, here are our variables separated. And then our boxes here, down in the very corner, we're going to have our our total population. Then this column is going to be the total number of days predicted rain and the total number of days predicted no rain. And this total is going to be the total number of days that it didn't rain and the total number of days that it did rain. So when we are building our two-way table, the first place you want to start is with those variables. Then when we're filling it in, we want to begin with the population size, that total. So in this case, I'm looking for the number of days, the total number of days in my year. And so in a year, there are 365 days. So my population is 365. When you're filling in a two-way table, you want to look to see what is your population size. What is your total number of things that you're looking at? Do that first. Then once you've done that, then we can look at the prevalence of whatever's occurring or however many days there are. So in this case, we know that there were 5 days that it rained each year. So out of those 365 days, I know a total of 5 days rained, which means that 360 days it didn't rain. I can just subtract to find that out. So I start with my population, use that prevalence to find out the number of days it rained. Then I'm going to read the rest of my information to find out some more. When it actually rains, the weatherman predicts rain 80% of the time. So he gets it right when it rains 80% of the time. He gets a true positive. It rains and he predicts rain 80% of the time. So I'm going to do 80% of 5. Remember that percent is always out of 100. So we could make this 8/10 times 5, which is 40 over 10, or just 4. So 4 days that it rains, he predicted rain, which means one of those days that it rained, he predicted no rain. Then it tells us that 10% of the time when it doesn't rain, he says it does rain. So 10% of the time that it doesn't rain, so 10% of those 360, remember with 10% it just takes and moves that decimal over one spot to the left. So 36 days, he's going to say that it does rain. 36 out of those 360 days, he says it does rain. So throughout the year, he says it rains a total of 40 days. even though it only rained 5 days, he predicted rain 40 days. That means that here he said that, well, let's see, 20, 24, that's going to make that 60, 10. So 324 days, when it doesn't rain, he predicted that it didn't rain. And that makes a total of 325 days throughout the year, he predicts no rain. Now I can kind of check myself. It should add this way, add that way, add this direction. Sure enough, it does. So there we've got our two-way table. Then we can begin to look at the data and we can see how the two variables are related. Math Made Simple at Simpson Math. Thanks for watching.